All right, thank you so much for joining once again. This session, we want to take a deep dive into what we call hypothesis testing. It's quite, it's a continuation from the sampling distributions that we've been doing, in the sense that what you learned from last week, you're going to use some concepts to do whatever you're going to do today. And it's very practical, it's fun. And as you've always seen, quantitative methods or business math or anything that has to do with business, you first have to look at it's just our normal life applications that we use mathematics to do. So basically, what we'll be doing today is just another extension of what we've been doing at all times. So after the end of this course, you should be able to learn how to formulate null and alternative hypothesis and how you apply this in a single population mean and how you apply it in estimating a single population proportion. You know how to formulate a decision rule, you know how to use the test statistic, you know what we call type 1 and type 2 errors, and then you know how to compute the probability of a type 2 error. I hope I'm not going too fast. All right. Now, these are your reading lists, chapter 9 of Grosvenor, Shannon, Fry, Smith, and then chapter 9 of Anderson, Sweeney, and Williams. You could have a look at it and then you see how that also works for you. Okay, so most of the time, we make a lot of inferences based on sample. Last week we discussed some of the importance of sampling, and we talked about we also talked about statistical inference, where we make conclusions on the population based on the sample. Okay, so most of the times we make claims, and these claims are very emphatic claims about a certain population. And when we want to prove or test our claim, we mostly want to use a sample data to test our claims, right? Now, the claim that you are making, or the conjecture that you are making, or the assumption that you are making concerning the population is what we are terming as a hypothesis. Okay, so a claim or any conjecture that you make concerning a population is a hypothesis. So I can say that unemployment rate is 50%, or graduate unemployment rate is 50%, in the sense that I'm trying to give you an indication of how many of all university graduates are unemployed. Okay, now I've made a very emphatic statement, I've made a very huge claim. Okay, and that claim that I've made is what I'm terming as a hypothesis. Okay, so the hypothesis is a claim that is made, okay, about a population parameter, not about a sample statistic, but it's a claim that has been made about a population parameter. That is what the hypothesis is about. So we don't make claims about a sample, but we make claims about a population. And some of these examples are here. The mean monthly cell phone bill is 42 cities. That's a statement. That's a claim. That is a statement or a claim about the population parameter that we are making. So as I was saying, these things have to do with claims that are made about the population parameter. Like the example you are seeing, the mean monthly cell phone bill of this city is 42. So that is a population parameter, right? And we also make a claim about the population proportion. The proportion of adults in this city with cell phones is 0.68, or about 68% of adults in the city with cell phones. So these are all claims that are made about the population parameter. And as I said, we can't make a claim about a sample statistic. Okay, we make the claims about the population parameter. And in hypothesis testing, okay, there are two statements that we make. And this is where, if you've never paid attention, this is where you pay attention. Okay, we have what we call the null hypothesis, and we have what we call the alternate hypothesis. Okay, so we make two statements about a parameter, the null and then the alternate. Okay, now in the null hypothesis, what we are doing is that we are stating what I will call the status quo. Okay, so the null hypothesis states the numerical assumption that is to be tested. Okay, um, in testing the null, or in formulating your hypothesis, you want to begin that the null hypothesis is true. Actually, the null hypothesis is always what is upheld, okay, before there is a claim that allows us to say otherwise. For instance, um, someone should answer this for me, and you can write it in the chat box. How many months does it take for a normal human being to go through the process of pregnancy and till labor, as in the gestation period of a human being? Yes, it's 9 months. Very good, right? So if somebody makes a claim, okay, that gestation period is no longer 9 months, but it's more than 9 months, or it is 12 months, or it is 15 months, okay, that person has made an emphatic claim that needs to be tested with evidence. Do you get it? Now, what is required is that the null hypothesis in this claim is the status quo. And what is the status quo? The status quo is that gestation period is 9 months. Okay, so before you should tune our minds to another assumption that gestation period is not 9 months, then you should have enough evidence against the status quo, right? So we need to know what the status quo is. And the status quo is what is represented by the null hypothesis. Okay, now the null hypothesis always contains expressions like equal to, less than or equal to, or the greater than or equal to sign. So what it means is that the null hypothesis always has strings of equality. Okay, they always have strings of equality. And the null hypothesis may be rejected or it may be retained, as in it may not be rejected. Okay, so if we do not have enough evidence to prove our claim, then we are not going to reject the null hypothesis. If we have enough evidence to prove our claim, then we can reject the null hypothesis. So if this person has enough evidence to tell us that gestation period is, let's say, 15 months, okay, then this person is able to twist and turn our minds to the fact that, okay, we're all being lied to, or we're all being misled when they told us gestation period is 9 months, but it's actually 20 months, right? Or 15 months, or whatsoever month. Okay. But if the person doesn't have enough evidence to prove his claim, then we come back to say that, please, what you said wasn't even true. So we come back to our usual thoughts that gestation period is 9 months. Okay. Now, you need to understand the differences and what really the null hypothesis does, so that you'll be able to formulate some of these hypotheses when it comes to testing them. Okay. Now, as I said, the null hypothesis always possesses certain strings of equality. So it has the equal to sign, the less than or equal to sign, and then the greater than or equal to sign. Now, the alternate hypothesis is just the opposite of the null hypothesis. Okay. The alternate hypothesis would be the challenge, okay, against the status quo, and mostly it's always it's what is believed or by the researcher. Okay, now it is what is believed by the researcher, because I mean, if you are testing the status quo, or if you are just proving that the status quo exists, there's nothing interesting about it, right? If a doctor comes to say that gestation period is 9 months, there's nothing interesting about it, okay? Because we know. You get it? But if somebody comes to say that no, the gestation period is not 9 months, then there is something interesting about it. Then we want to know, why do you think it is not 9 months? Why do you think it is 12 months? Why do you think it is this? Which evidence do you have? Okay, so most researches and most of the things that we do are things that seek to challenge the status quo. Okay, so the alternate hypothesis is always the opposite of the null hypothesis. So in the alternate hypothesis, you see stuff like the not equal to sign, you see the strictly greater than sign, and then you see the strictly less than sign. Now, where we have the null hypothesis having an equal to, its corresponding alternate hypothesis will have the not equal to sign. Okay, where you say the direct opposite, you get it. Where the null hypothesis has a less than or equal to, its alternate hypothesis will have a strictly greater than. Okay, and then if the null hypothesis has a greater than or equal to, its alternate hypothesis will have a strictly less than sign. So there are certain statements that we will check, and then you would know, and you can formulate. Okay. So this is let's spend some time in learning how to formulate the null hypothesis. Okay. Then we can be sure of 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 your knowledge in null and alternate hypothesis, and then we can move on. So let's see if I can get you some questions, and then you'll be fine. All right. So this one question: the packaging division of a warehouse, right, of a factory. We want to know if bags of rice are filled according to the 5 kilograms target, or significantly below or above the 5 kilograms target. Now, I need a volunteer, 2 people to help me with the class. Any hands up? Okay, Emmanuel, and then Maureen. All right, all right. So we can unmute. Okay. So Emmanuel, I'm just going to ask very simple questions about stuff that you already know. All right. So Emma, when you buy a 5 kilogram bag of rice, right? What do you expect the weight to be?
5 kilograms.
You expect that the weight should be 5 kilograms, right? So
Yes.
is 5 kilograms, isn't it?
What do you mean?
The status quo is 5 kilograms, isn't it?
Yes.
Yeah,
Yes.
very good. So if we want to test whether, if something is wrong with the packaging, okay, if something is wrong,
Okay.
what do you think would happen to the eventual weight of the rice?
I think the weight of the rice will reduce.
It will reduce. Will it only be the case that it will reduce?
No, it can also increase.
It can
But
also,
I think mostly it should rather reduce.
no, let's stick with the fact that it can either increase or reduce.
Increase, okay. All right.
There's something wrong with the packaging machine. It's either the machine will fill more than 5 kilograms, or the machine will bag less than 5 kilograms, isn't it?
Yes. Yes.
What it means is that if I want to test, look at the question here, and Maureen, you would answer me here. If I want to know if the bags of rice are filled according to the 5 kilograms targets, that's the status quo, or significantly below or above the 5 kilograms target, then what we are looking out for is evidently, we don't care whether the filling was above or below the 5 kilograms target, is right. What we care about is that the thing didn't fill a 5 kilograms. Okay, so the now or the status quo is that the the average weight is 5 kilograms. But the argument against the status quo is that the average weight is what? Is not 5 kilograms. Is that okay? Okay. So basically, what we have here, okay, Yeah, so I'm trying to go over the hypothesis again. I'm using the example so you can take note of that. So what we have here, that your null is the status quo, which is the 5 kilograms, and the alternate is the argument against the status quo that the machine will not be working properly, so it may not be bagging the 5 kilograms. So it is what not equal to 5 kilograms. I remember how we are formulating it. We normally use H0 to refer the null to the null, and then we normally use HA to refer to the alternate. So H0, that is the null, is such that the population mean is equal to 5 kilograms, and the alternate is such that the population mean is not equal to 5 kilograms. Now let's take another example. The waiting time at EcoBank branch on Monday to Wednesday is approximately 15 minutes, which management would want to maintain or improve upon. Therefore, occasionally, management randomly picks customers and track time spent when they enter the bank, when they are served. Okay. Now, because if Maureen, if a bank wants to improve upon their waiting time, what do they really want to do?
If they want to improve, it means they want to make sure that customers don't spend more than 15 minutes there. So if it can be significantly lower, that would be good.
Exactly. So if I want to improve my waiting time, then I expect that my waiting time will be what? Significantly reduced. Okay. So the status quo is that, I mean, tell me the truth. If you go to a bank, okay, especially, okay, I don't want to mention any other bank. We are having this YouTube. Okay. So if you go to a bank, right, any typical bank that you go to on a typical rush hour or on a typical end of month or beginning of month or a weekend before a holiday, right? You see a lot of people at the bank and you don't spend more than less than 15 minutes, right? So the status quo here is that the average waiting time is more than 15 minutes. It's actually 15 minutes or more, okay? But they want to improve upon it. So they are challenging the status quo that is more than 15 minutes. So the alternate hypothesis here is that the average waiting time is what is less than 15 minutes. Okay, so it's always easier to look at the claim or look at what is the challenge against the status quo. Once you get that, you can use it to formulate the status quo. Because I told you that if the status quo is equal to, its alternate will be what? Not equal to. If the status quo is greater or equal to, the challenge against the status quo will be strictly less than, right? And if the status quo is less than or equal to, the challenge against the status quo will be greater than strictly. So those are some of the things that we would be looking at. Okay. Now here, occasionally the management will pick random companies. So we have the status quo, and only if the sample mean waiting time is substantially greater than 50 minutes will EcoBank reject the null hypothesis. So this question actually is telling us that they want to do something about it, and they first want to test whether the waiting time is substantially greater than 15 minutes. They want to test whether the waiting time is substantially greater than 15 minutes. So if they want to test that the waiting time is substantially greater than 15 minutes, then it means that the alternates will be greater than the status quo will be less than or equal to. All right. Now, because we are dealing with okay, so I think we can have some examples to begin with. Let me see where the examples are. Just a minute. Okay, so we have some examples to go through, and let's see how they can be done. All right, so okay. CompuSoft, a computer processor, claims that its newest okay, this is a two sample case. All right. Prospective salespeople for an encyclopedia company are now being offered a sales training program. Previous data indicate that the number of sales per month for those who do not participate in the program is 33, right? To determine whether the program is effective, a random sample of 35 new employees is given the sales training and then sent into the field. 1 month later, the average and the standard deviation for the number of sets of encyclopedias sold are 35 and 8.4 respectively. Do the data present sufficient evidence to indicate that the training program has enhanced sales? Now, we are not in this stage, we are not interested in how to solve, we are not there yet. But all I'm interested in is how we can formulate this, this hypothesis. Now, we want to find out whether the training program has enhanced sales. Okay, Maureen, what does it mean to say that the training program has enhanced sales? If sales has been enhanced, what do you expect to see in this question? Oh, everybody went off. If sales have been enhanced, what do you expect to see? Okay, if your hand is up, Makati, if sales have been enhanced, what do you expect to see? Okay, someone, yeah.
So it means that sales has increased.
It means that sales have increased, right? So
yes,
relative to the previous data, okay, relative to the previous sales, what was the previous sales, the average sales? What was the average?
33.
33, yeah.
Very good. So if sales has been enhanced, then what do you expect to see? Okay, yes, Emmanuel, if sales have been enhanced, what do you expect to see?
Something higher than the 33.
33 is what is higher than 33?
Yes. Yes.
Okay. Yeah. David, your hand was up. Is there any other different response?
Okay,
very good. So if sales has been enhanced, then you expect that the company or the set of sales will be what? Higher than 33. So what is going to be the alternative hypothesis? Can you write it mathematically for me in the chat? What is going to be the alternate hypothesis? If mu is the average sales that is recorded, what do you think will be the alternate hypothesis? Very good. It means that Lucille says that the alternate hypothesis of mu is greater than 33, right? Mu is greater than 33. So what will be the corresponding null hypothesis in this situation? What will be the corresponding null hypothesis? Mu is less than or equal to 33. So Leroy, that's not how we write the null hypothesis. It's not H0 is less or equal to 33, but it's H0, this is how we write it. So the null is such that, let's say mu is less or equal to 33. Then the alternate will be such that the mu is what? Greater than 33. Okay. If you write H0 is less or equal to 33, that is wrong. Okay, so take math as a language that we are speaking. Okay, so if you write it like that, then that's more like a PG mathematics that we are speaking. So it doesn't really hold much. All right, thank you. So these are some of the things that we want to do, and we want to also get that. Okay, let's look at number 4. Number 4, film production companies are gravitating toward Kumawood, where the film production facilities are less expensive than Gollywood. Now, a sample of 20 soundstage facilities produce a mean rental price of 3.77 and then a standard deviation of 0.87 in Kumawood. For Gallywood, a sample of 22 produced a mean rental price of 4.2 and standard deviation of 0.5. Now, do these statistics provide sufficient evidence for the film companies to gravitate towards Kumawood? Once again, forget about the numbers that we are building here. Think of this, what the question seeks to provide. Do these statistics provide sufficient evidence? Now, I want someone to help me. Yes, someone, before you ask your question, you will help me with this, with answering this question. Okay, since your hand is up. Okay, I have a lot of people whose hands are up this morning. Okay, so let's see. Someone is not responding. Yes, Emmanuel.
Yes.
Yeah, do you have a question or it's just a clarification or we are moving on?
No, please, sorry, it's an old hand, sorry.
Okay. But you stay on. Okay.
All right.
Hello? Okay, so I think their hands are not up. Michael?
Hello, sir.
Yeah, do you have a question?
No, I wanted to assist.
Okay, that's great. Then stay on. That's fine. So, okay, yeah. So, Michael, that's the question. I was saying that we want to find out, do these statistics provide sufficient evidence for film companies to gravitate towards Kumawood? So we have two production companies, right? We have Gallywood and then we have Kumawood, right? The claim is that people are moving to Kumawood because film production facilities are less expensive, right? Now, if I want you to formulate an alternate hypothesis for this situation, forget about the numbers, right? What do you think would be the first thing that will come to mind? What are you comparing, first of all?
I'm comparing the movement of people from Kumawood to Gallywood.
Mm-hmm.
So, and for me to create an hypothesis, alternate hypothesis, I would say that people are not moving. People are moving to Gallywood not because of the facilities being less expensive, or people are not moving to Gallywood at all.
So what is causing them to move?
Maybe something else aside the facilities.
No, but the question is emphatic about the facilities, right?
Mm-hmm.
Mm-hmm. So what is causing them to move is really the facilities. Okay.
Right.
Eugenia, do you have any other explanation that you want to give? Yeah.
No, it's more like a question.
Okay, you hold on with that thought. Let's exhaust this one and then we come back to your question. Okay. Now, since your hand is already up, what do you think about this one?
What do I think about it?
Yeah.
I think that looking at the question, the increase of people moving from the Gallery to Kumawood is high. So maybe the Null hypothesis with the mu is greater than, like, yeah.
Okay.
Yeah, but
I think we need more explanation. Okay, last
yeah.
one. Please. Yes. Hello?
Yeah, hello sir.
Yeah, Eunice.
Yeah, hello, sir.
Yeah, I'm listening.
Yeah, certainly. So, it shows that the people are moving to Kumawood because the film production facilities are less expensive.
Exactly.
So that would be the now hypothesis.
Okay.
Stating the fact that it's less expensive, so more will go to Kumawood. So it will be more over there at the initial.
Okay. You have an idea about it, but I think the expression is not really coming out so well. Michael, let's take Michael. That's it. Yeah.
So I'm here.
Yeah, please continue. Yeah.
So please, I thought we are done. I was the one who started with who you started with.
Oh, okay, okay. Okay, so let's move on. Now, what we are dealing with here are two different groups. We will do two sample into detail. We are looking at Gallup, right? The Majis, the Absalom and stuff, the Frank projects, and then we are looking at Kumau, the Danfugies and Co. Now, you're saying that people are moving because film production facilities are less expensive than what? That of what? Gollywood. Okay. So what we are testing for here is testing the claim whether the film production facilities in Kumawood is significantly less than the film production facilities in Gollywood. Okay. So if I am formulating, then I say that maybe, let me say that maybe how do I call it? Mu, let's say sub G, okay, be, let's say the average cost of facilities in, let's say, Galo, right? And then I would say that perhaps let's mu sub K be that of Kumawood. Okay, so what you want to see, okay, is that if this is the claim of the people as true, then you expect that the average cost, okay, of facilities in Kumawood is significantly less than the average cost of facilities in Gollywood. Okay, this is the claim that you'll be testing. Now, because this doesn't have any equality or whatsoever, this is the claim. So this becomes your alternate hypothesis. So if this becomes your alternate hypothesis, then your corresponding null hypothesis is actually this. Okay, that. So this is what I was looking for. You are comparing two groups stage facilities. So the average cost in Kumawood against the average cost in Gollywood. And this is how you would formulate that. So this becomes your H naught. And then this becomes your alternate hypothesis. Okay. Now, one key thing about hypothesis testing, okay, what you need to do is your ability to formulate it is good. The calculations aspect, everybody can do it, okay? But if you would make the wrong hypothesis, although your calculation could be correct, it can lead you to the wrong conclusions. Okay, so you have to take note of that. That is a very important thing that we need to take note of. So yes, somebody is asking whether does it mean that you always have to formulate the null and then you have to formulate the alternative first? No, not necessarily. Okay, what I'm saying is that for me, I believe that it's an easier way to know the kind of claim that people are making. Okay, so if you do that first, you'll be able to know the corresponding null. As you advance and become more expert in how to formulate hypotheses, you will see how easy this thing would come to you. So you don't need to worry about that. Okay, Eugenia, your hand is up. What's up?
Yes, sir. Please, the first question we tried from the questions you brought. Can you please explain it again? The 33, the one that you said mu was less than 33.
What's the problem with that? Maybe if you tell me what problem it is.
Okay, I was thinking that maybe the now was greater than 33, but after doing it, so I didn't really get it.
So
Yeah.
we're looking at the claim, right? Do the data provide sufficient evidence to indicate that the training program has enhanced sales? Okay, so if you want to find out whether the program has enhanced sales, then it means that after the program, you expected that the average sales would be more than what they used to have before. Do you get it?
Yes, sir.
So your alternate was going to be that the average would be what greater than
Okay.
33. Do you get
Okay.
it?
Yes, sir.
Very good. That's the claim that they are making. And because it is enhanced, that means that it is more, strictly more than what we had before. You get it? So if the alternate is greater than, okay, then its corresponding now will just be less than or equal to. That is what we are saying. Do you understand?
Oh,
Yeah.
yes, sir.
Right.
Thank you very much.
All right. So we can move on. Right. Good. So what we are So how to formulate hypothesis is very key. You should take note of that. Now remember that what that we are doing is just based on our sample data. We are making inferences, and last week we learned about some of the dangers in using only sample estimates to make inferences about your population. Yeah, it can be that dangerous. So what can we do? We are prone to errors, isn't it? There's always the chance that we can make an error in our conclusion. If you don't take the right sample, if you don't take the right sample size, a lot of things can give us a lot of errors. So indeed, different samples will give different values, of course. And therefore, result based on samples could technically give results that are quite different from the mean. You get it? So, for example, we can make a claim about the null hypothesis, and that claim will not be true. Okay, and it can be rejected. Okay, now let me just read what we have here. So, for example, the null hypothesis about the population could be true, but due to result from a sample, it could be rejected. So there's a chance that you can reject a null hypothesis which was actually true. Okay, and there's also a chance that you can reject an alternate hypothesis which is actually true. Okay, you can say something about somebody which is actually not the case. Or in this case, we are making a false accusation, or like how the Bible will place it. You are giving a false witness about the person. Yet you've made a claim, you've made a statement. Why did you come to that conclusion? Perhaps you saw the person in a certain position that has changed your perception about the person. Okay, so you are basing your mind, your conclusion on what you saw, and it could be false, it could be untrue, it could be any other thing else. It could mean something different. Okay, but that's the sample you have, and that is the conclusion that you have come to. So in this case, you've made an error in your judgment. So basically, there are two main types of errors that we make when we are forming a hypothesis. We have the type 1 error, and then we have the type 2 error. Okay, now I'm going to use a scenario to um, to illustrate my position. Okay, so once again, I want you to be very attentive. Okay. Any volunteer to help me? Mostly the usual hands, but today I want somebody new. Any volunteer? Please hurry up. We are not. We are far behind time, so just raise your hand and then let's go. Otherwise, I'll choose. Okay, Grace. Yeah. All right, Grace.
Sir,
Yes, you can hear me, right?
yes, please.
Have you been to a court before? Have you witnessed
Court?
before? Yeah.
No, I've not been to a court before.
You've witnessed proceedings before on TV.
Yeah.
Right. What are the things that the judge can do?
You can either declare someone as guilty or not guilty.
So someone can be guilty Let's put it here, right?
Mm-hmm.
Or someone can be not guilty, right?
Yes, please.
Okay. But can the judge be erroneous in his or her judgments?
Pardon.
Can the judge make a mistake? Can the judge make an error
Yes, please.
in his or her pronouncement? How?
The person probably could be innocent, but you would declare him guilty.
The person can be innocent but will be declared guilty, isn't it?
Yes, please.
So let's say something. The person can be, hold on, let's see. The person can be innocent or the
Yeah.
person can be not innocent, isn't it?
Yes, please.
Okay. Now, if the person is guilty, if the person was innocent, okay, but
Mm-hmm.
pronounced guilty, is that a correct decision or a wrong decision?
A wrong decision.
It's a wrong decision. So let's put this one here. Wrong decision. Okay. If the person was not innocent, okay,
Mm-hmm.
and is pronounced guilty, is that a correct decision or a wrong decision?
It's a correct decision.
Correct decision. So, okay. What if the person is innocent and is pronounced not guilty?
Is innocent is correct.
So correct.
Yeah.
Correct decision. And then the last one, innocent.
It's wrong.
So it's wrong decision. So how many wrong decisions do you have?
2.
2, right? Now,
Yes, please.
what are they? What are they?
Wrong. Innocent and proven guilty.
Innocent but proven guilty, right?
Yes, please.
And not innocent,
Yes.
and then you are acquitted and discharged. Now,
Yes, please.
which of them is very grievous, is very sad, is very harmful? Although the two of them are wrong, but which of them is very grievous?
I think both depending on the stand of the person.
Yeah,
For the one who is innocent and declared guilty, it's very grievous that someone who is innocent has been proven guilty. But for the one who is not innocent and has been let go, to be grievous to the society, is going to commit more atrocities.
okay. But the way you're explaining it, you are not sticking. And yes, class, I also want you to choose. You can give me your answers in the chat. Between innocent and an innocent person who is being proven guilty and is maybe sentenced or whatsoever, and between someone who is actually not innocent, the person is actually committed a crime but has been proven not guilty. Which of them is very grievous? Yeah, Grace, your last one.
Innocent but guilty.
Innocent but guilty, right?
Yes,
So,
please.
I mean, we have a lot of criminals walking along our streets every now and then, right? We live with them. But since we've not been able to find any evidence to charge them for their crime, we do not really have to put them in jail, right? But it's worse off if someone didn't commit any crime and the person has been put in jail. It's sad and it's very how do I put it? It is something that really harms the person's personality. Goes to jail, comes back having nothing to do because you are declared as an ex-con, although you didn't commit any crime, right? And there are a lot of people in prison for such reasons. So innocence and proving guilty is really a very grievous offense, right? Not an offense, but it's a grievous situation that you find yourself in. Now, likewise, okay, so for everybody, before you are proven guilty, You are first innocent, isn't it? That's why the court has
Mm-hmm.
statement like you are innocent until proven guilty. Okay, so
Mm-hmm.
status quo is that you are innocent. Okay, you are only proven guilty if there are evidence against you, isn't it? There's enough evidence to put you behind bars. That is when you can be proven guilty. And that's why we see a lot of people, the person committed the murder, but the person is proven innocent, not guilty, because we don't have enough evidence to convict the person. Right. So, in the same way, the status quo, being innocent, can be referred to as a situation where the null hypothesis is true. Okay. And guilty is where you reject the null hypothesis. So, in a sense that if the null hypothesis is true, but you reject it, you've made a wrong decision. Now,
Mm-hmm.
if the null hypothesis turns out to be false, and then you reject it, you've made a correct decision. Okay.
Mm-hmm.
If the null hypothesis is true and you fail to reject or you retain it, right? You've made a correct decision. And if the null hypothesis is false and you fail to reject it, you've made a wrong decision. Okay. But we believe that if you reject the true null hypothesis, you've made a very grievous error than even failing to reject a null hypothesis. Reject the true null hypothesis. What it means is we are trying to tilt our minds from what we had known previously. If someone comes to tell you that 1 + 1 is no longer 2, but it's 5, and the person is able to prove to you that it is 5, and later you find out that, oh, what you did was actually 2, the person has caused an error because the person has diverted our minds away from the status quo, when in actual fact the status quo was true. Okay, so we call this error, okay, rejecting the true null hypothesis. We call it a type 1 error. Okay, and then also if a null hypothesis is false and then we fail to reject it, we call that one also a type 2 error. Type 2 error. So basically, what we are saying is that a type 1 error is the kind of error that is committed when you reject a true null hypothesis. And it's a very serious type of error. Okay. And the probability of rejecting it, of committing a type 1 error is alpha. Okay. And mostly we term that alpha as what we call the level of significance. If we were in class, I would have asked you to repeat. So please, wherever you are, just repeat after me, level of significance. Very good. So the level of significance is actually set by the researcher in advance in such a way that the person wants to minimize. So we actually work in hypothesis testing in such a way that we want to minimize our chances of committing a type 1 error because that's a very serious error. Okay, so we give out a certain level of significance to work with, and then we work in such a way that we want to minimize this level of significance. Now, if we fail to reject a false hypothesis, that's a type 2 error, and that probability is what we term as beta. Okay, so this is what I think we've done. These things. The H0 is true or H0 is false when you make a decision to reject or not to reject it. These are some of the things that you need to take note of. Yeah, so you might have committed a type 1 error or you might have committed a type 2 error, depending on where you find yourself. Okay, we move on. All right. So let's talk a little bit more about the level of significance. Is the probability of making a type 1 error. Okay, and that is when the null hypothesis is true and then you are rejecting it. Now, what we are looking at in terms of the type 1 error identifies what we call a rejection region, which you would see as we move on. Okay, and mostly we use values such as 1% or 0.01, 5%, 0.05, or 10%, which is actually 0.1. Okay, and the level of significance is selected at the beginning, so you would know about it as we move on, and it helps you have an idea about what we term as the critical value of the test. You'll get to understand all of this when we are doing more examples with regards to hypothesis testing. Okay, all right. Okay, so I spoke about the rejection region. Now let's take a look at something. Yeah, in a hypothesis test, for say a single population mean, X bar is used to test the population, the hypothesis under consideration. However, note that even if H naught is true, it is possible that there are some values of X bar that will support the alternate hypothesis. As I said, the hypothesis test depends largely on the sample that you would end up selecting. So there will be certain points that, in fact, your H naught could even be true, but because of the sample that you picked and the kind of sample you picked, the sample statistic will lead you to conclude in favor of the alternate hypothesis, right? So we need to give room, an allowable room for error, okay? But given that you have an allowable room for error, okay, you want to find the probability of rejecting the H0, okay? And that probability is what we are terming as the alpha. We don't want to give so much room for error, but we just want to give a certain allowable room for error. Okay, so in a typical normally distributed and random variable, and I believe you have your normal distribution tables here, we want to find two things. We would see what we call the rejection region, and then we would also see what we call the acceptance region. Okay, so if the statistic, or in this example, we have mu is equal to 25, and mu is less or equal to 25 for the null, and then we have mu is greater than 25 for the alternate. Now, if the statistic that we are looking for falls in the rejection region, which is indicated with the shaded portion over here, then we can conclude that your null hypothesis is true. Okay, but if the statistic falls outside of the shaded region, then it means that we are not going to reject the null hypothesis. Okay, now the chances of making an error where a true null hypothesis is rejected is what we are going to term as the significance level. And you don't need to calculate any significance level. These things are given to you. So if you're a researcher, depending on the sensitivity of your research, you determine what the level of significance is. Otherwise, if it's an exam or anything, you will be given a level of significance. But largely, most of the time, we work with a 5% level of significance. That is an alpha, which is equal to 0.05. Okay. Now, there are, as I mentioned, what we call the significance, and then the rejection region, and then the acceptance region. But also there are several forms of tests. There are three main forms of tests that you will be doing. We have what we call the lower tail test, okay? And in the lower tail test, we are always interested in testing the null hypothesis, the alternate hypothesis that involves a less than. Okay, if, and you have to listen here, and if your alternate hypothesis involves a less than, then it means that the critical region or the rejection region, the area that will lead you to reject this null hypothesis, is always to the left of the standard normal distribution curve. Again, we will have more examples to explain what we are saying. Okay, then we have the upper tail test. Okay, the upper tail test has the alternate hypothesis defined by a greater than sign. Okay, and that tells you that the statistic or the rejection region falls to the right of the standard normal distribution curve. Okay, then we have the two-tailed test. Now, the two-tailed test has the non-equal to sign as the alternate hypothesis. And here we divide the alpha, which is the level of significance, into two. One falls to the left of the normal curve and the other falls to the right of the normal curve. Now, practically, these things mean a lot. Okay, the lower tail test and then the upper tail test is what we generally would term as a one-tailed test. One-tailed test. Then the two-tailed test, yeah, is actually called a two-tailed test. Okay, that is when we have the non-directional. You don't know whether it is less or it is greater. Okay, it is the same as a two-tailed test. Now let's take this example, and this is a very simple example that I feel all of you will be used to, right? Now let's take, for instance, a lady goes to the salon, right? The lady does a new hairstyle, okay, and maybe a guy should help me out here. Can any guy volunteer to help me with this? All right, David, thank you. David, you can unmute.
Okay.
Very good. Now, David, assuming your lady, I don't know, but assuming a lady or your friend comes with a new hairstyle and tells you, how do I look, right? If,
Yes.
on what circumstance will you base to say that she looks nice?
On what circumstances?
Yeah.
Ordinarily, I can't say she doesn't look nice. So
What?
ordinarily, I can't say she doesn't look nice. So I'll just go ahead straight away and say that.
So when she tells you she looks nice and genuinely, when she asks you how do I look and genuinely she looks nice, you tell her she looks nice, isn't it?
Yes.
Yeah. Why would you tell her she looks nice?
Probably because her hair is pretty.
Because the hair is pretty, or because her look before the hair is, or her look after the hair done is better than the look before, right?
Yes.
So if beauty before is great, beauty after is greater than beauty before, then she looks nice, isn't it?
Yes.
Very good. So that's, in that sense, it's an upper tail test because you are testing the null hypothesis whether beauty after, right, is what greater than beauty before, isn't it?
Yes.
Now, assuming you are the very carefree, you speak your mind, okay? You say what you want. You don't care about anything. You're not diplomatic about anybody. And you realize that, okay, Charlie, the girl is not looking so nice. I mean, the person should have just kept the old hair, right? When she asks you, how do I look? What would you answer? Based on the fact that I said you are very carefree.
Oh yeah, that I'll go straight and say, you look better than, you look more beautiful than now.
You don't look nice. That
Yeah.
is very good, right? On what basis are you doing this? Because the beauty
After is
less than
lesser than
beauty,
beauty before.
right? And that is identified by the lower till test. Do you get it?
Yes.
Very good. Now, what if the truth hurts, but you don't want to say it? Okay.
Yes.
But you also want to say something about the hair because she has asked you, David, how do I look? What will you-
I'll say, well, the hairdresser did well, but I think she could have patched this place a bit or done this a bit to this side.
But if that person says that, the lady will still feel like, oh, you are just trying to tell me that I don't look nice.
Oh, I'll say you look nice, but they are faults. So that one, I think, so it will be, I'll try and distribute it evenly.
Now you are trying to be diplomatic, too diplomatic. Okay, I mean, what you can say is that, wow, you look different, right? When you say you look different, you have absorbed yourself from whether the person looks nice or not. The point is, the person doesn't, you've not told the person whether the person's beauty is worse after than before, or the person's beauty is better after than before. All you have said is that, Charlie, you look different. Okay. And if you tell somebody that the person looks different, well, you've said something, but you've not said anything. You get it? But all you are saying is that the person is not the same as she was in the beginning. Okay. So in that situation, you are dealing with what? A two-tail test. Okay.
Okay.
So I'm giving you
So please, can I ask a question?
yes, please.
So in this instance, if you ask me how do I look, and I want to talk about the two-tailed test, I can say not bad. What does that mean?
No, not bad. Not bad doesn't mean you look different. Okay.
Does it also mean you look good?
No, not bad kind of means you look good. Just that maybe it could have been better. You get it? But
Okay.
we are looking at the situation where you do not stick yourself to a certain direction. So
Okay.
I know that beauty, what I can see, I can't describe whether you look good or you do not look good. But what I can say is that you do not look like the way you used to.
Okay.
So if beauty after is not the same as beauty before, and you want to really absorb yourself as to whether it is true or not, as to whether you don't want to commit yourself to all of these things, then you can just tell the person you look different. Okay. In the two-tailed case, okay, we are looking at a non-directional situation. Okay. And it like in the packaging question that we had, we found the situation as to whether the packaging was done right or the packaging wasn't done right, and we're interested in whether it was more than 5 or it was less than 5. So if it is less than 5 kilograms, it is not done right. If it is more than 5 kilograms, it's not done right. If it is equal to 5 kilograms, it is done right. So we'll be interested in the two-tailed test kind of hypothesis testing. And given these situations, they have different ways of solving them or approaching the solution. Okay. All right. Okay, so let's move on. All right, so we have several ways of doing a hypothesis test, and the mathematics will come soon. Okay, but I think we need to take more time to explain before we do the math, so that you can get to understand. So you convert the sample statistic to the test statistic. There's something we call a test statistic or a critical value approach. So in the critical value approach, we need to find what we call a test statistic. The test statistic is what we are going to use to really identify or to really show or prove that our null hypothesis should be retained or should be should be rejected. Then we need to determine what we also call the critical value, which we will. And then we compare the critical value to the test statistic. And if the test statistic falls in the rejection region, we reject the null, otherwise we do not reject the null. Okay, so these are some of the things. So let's take, we will take an example, and then we would have a look at what we want to do. And so in a one-to test, there's only one cutoff value. There's only one critical value. In a, yes, also here, there's only one critical value. But in a two-tailed test, there are two critical values. I'll come back to this, and then you will see how to explain the thing. Then, in testing the hypothesis, these are some of the things we are going to consider. We are going to consider the situation where the population standard deviation is known, and we will consider the situation where the population standard deviation is unknown, and we will consider that for large samples and also for small samples. So basically, that is what we are going to do. Now, what we would consider is that whether it is known or unknown, the test statistic that we would compute is going to be different. There will be different ways of computing the test statistic, and each of them also would follow a different probability distribution. Okay, each of them will follow a different probability distribution. So if the population standard deviation is known, okay, then this is how we would calculate the test statistic. If you remember the sampling distribution, nothing much has changed. So it is the mean, the sample mean minus the population mean divided by the standard deviation divided by the square root of n. Okay, and that follows what we call the z distribution. The z distribution is the same as the normal distribution, the standard normal distribution, the ones that we did when we were considering sampling distributions. Okay, so it is the z distribution or the normal distribution that will help us to calculate what we term as the critical value. Okay, now in the situation where the population standard deviation is not known, okay, in the situation where the population standard deviation is not known, then if the sample size is large, then we are going to still use, we are not going to use this one, S bar minus mu, but because the population standard deviation is not known, we are going to use the sample standard deviation as an estimate for the population standard deviation. Okay, so if we do not know the standard deviation of the population, we are just going to use this sample value to estimate it. So you see that the only difference is in calculating the fact that instead of sigma here, we are using S, where S represents the sample standard deviation. Now, this follows a certain distribution called the T distribution. Okay, so we are going to have a T distribution table, or that we would read their critical values from. But the good news is, if the sample size is large, okay, whatever the distribution this is, whether T or F or whatsoever it is going to approach a Z distribution. So we can still use the normal distribution to calculate to determine the critical values that comes out of it. Okay. Now, if it is unknown and the sample size is small, then first of all, we have to assume that the population must be normally distributed, and then this is how we calculate the test statistic. The only thing that changes once again is that the sample standard deviation is replacing the population standard deviation. And it's as simple as that. And the distribution that it follows, okay, the sampling distribution is no longer a normal distribution, but a T distribution. We would take more examples of this. So we'll see what we can do. So let's go through the steps of doing a hypothesis testing or calculating the test statistic. First of all, we are going to specify the value of interest, okay, or the how do you call it? The parameter of interest. It could be mean of a population, it could be a standard deviation of a population or whatsoever. Then we will formulate the appropriate null and alternative hypothesis. Okay. We will indicate the desired level of significance. We will determine the rejection region. You compute the statistic, and then we will reach a decision and interpret the result. So look at these steps. Let's follow them squarely, one after the other. And I think that will clear whatever confusions that you have with regards to hypothesis testing. Okay, so let's solve this question. Okay, then you will see what we can do. Please, you should have your standard normal distribution tables ready so that we can go through. And okay, let me get the line. Test the claim, okay, that the true mean number of TV sets in Ghanaians' homes is at least 3. Test the claim that the true mean number of TV sets in Ghanaian homes is at least 3. Now, assume that sigma is equal to 0.8 and that a sample of 100 is taken and the sample mean is 2.84. Okay, so let's look at the parameters that we've been given. Anybody to help me with this question so that we can go through on a step-by-step basis. All right, Maureen, thanks. Okay, so what is the population value of, what is the parameter of interest that we are looking at for here? I know it is written here, but I just want you to assume the answers are not there. What do you think?
The number of TVs, the average number of TVs in Ghanaian homes.
Exactly. So we are not just dealing with the number of TVs in Ghanaian homes, right? But we are dealing with what? The average number of TVs in Ghanaian homes. Do you get it? Okay. So I would have said that let's maybe mu, okay, be the average number of TVs in Ghanaian homes. Is that right? Okay.
Yes.
Now, what are you looking at? We are looking at whether the average number of TV sets is at least 3. How do you write at least?
Greater than or equal to.
Greater than or equal to. So we are looking at greater than or equal to what? 3, right?
The 3.
And the moment you saw this greater than or equal to, what comes to mind? Is it the null or alternate?
That would be the null.
That would be the null, because we indicated that the null is what always has the strings of equality amongst it. Do you get it? So
yes,
we saw that the H0 is like that what? The mean is less or equal to 3. And then the HA is what? That the mean is greater than, sorry. So it's equal to 3 and then the mean is less than 3. Okay. What makes this a lower test, Maureen?
it's because the alternate hypothesis involves the less than sign.
Okay. It's because the alternate
The
hypothesis,
rejection region will be to the left.
yes, it involves a less than sign. So beauty after is less than beauty before, right? Good. Now, step 3 says that specify the level of significance. As I said, the researcher either chooses this or we give it to you. So here we are choosing an alpha equals 0.05 for this test. Okay. All right. Okay. So I think the main bone of contention is how we determine the rejection region. Okay. And that is where, as I will say again, if you've never paid attention, this is where you pay attention. Okay. Now, how do we determine the rejection region? Maureen, what is your understanding about the rejection region?
Okay. Please, with respect to what exactly?
With respect to the hypothesis testing. Okay. Okay, maybe I will explain something small to you and then. All right, so this is our normal distribution curve, right? And normally that is what we are dealing with. Now, if you have, as I indicated, the rejection region we are talking about, okay, is that region that allows us to reject the null hypothesis when the test statistic we will calculate falls within that region. Okay, so it's like a borderline. Okay, so before we can identify such a region, we need to identify a value, a critical value, so that if the statistic we will calculate falls beyond that critical value, then we reject the null hypothesis. If it does not, then we will fail to reject the null hypothesis. I hope that is okay. Okay, so we specify a certain region. Now, because this is a one-tail test, the rejection region, as I said, will be to the left of the normal distribution curve, right? So this is the rejection region that we are specifying. Okay, now this rejection region has this rejection region we see here. Okay, the area covered under this rejection region is actually the alpha. Okay, which is what? The 0.05. So the question is this. We go deep into the normal distribution curve, okay, to ask ourselves, what is the z value here, okay, that corresponds to an alpha value of 0.05?
Yeah.
Or what z value here will correspond to a probability of 0.05? I hope that is okay. So,
yes.
And let's go to the normal distribution table, and then let's see something. Table, right? Okay, I think I have to download it again. Right. So standard normal distribution table.
Please, does it mean that the alpha is always a probability?
The alpha is a probability, yeah.
Okay.
The alpha is a probability. Just take note of that. Very good. Okay, so we have the responsibility of going through this pool of numbers. Okay, what value are we looking for, Maureen? What value are we looking for?
We are looking for the critical value, the z value that will correspond with the 0.05. So we'll look in the pool of numbers and look for 0.05 and then trace it to the Z horizontally and vertically.
Let's look for a number that is either 0.05 or very close to 0.05. Okay, so let's see. So we have 0.054, 0.053, 0.051. We have 0.05050, right? And then
Yes.
we have 0.4947. At least in between these two numbers, we can have 0.05, isn't it?
Yes.
Okay. Now, what the value corresponds to this 0.05050? If you
Negative 1.604, negative 1.64.
Negative 1.64, and then which one corresponds to 0.4947?
Yeah, negative 1.65.
Negative 1.65. So you realize that the 0.05 lies between negative 1.64 and negative 1.65, right?
Yeah.
So sometimes we can take the average, okay, somewhere in the middle. So the Z score will be what? Negative 1.645. You get it? If you are taking the average, this is what is. So it's like 1.64 plus 1.65 divided by 2, isn't it? We didn't get the exact 0.05 from the table, but we found out that the 0.05 can lie between these two figures. And then the Z value that corresponds to it is actually 1.64 and then negative 1.65. So we assume that the actual value will be is closer to the average than just to the endpoint. So we take the average and we have actually is negative. So negative 1.645. So our critical value, okay, is what? Our critical value, negative 1.645. Do you get it? So when you go back to the slides, what do you see? You realize that if the test statistic falls below this critical value, so any number below negative 1.645 will lead us to reject the null hypothesis. Do you see that?
Yeah.
And then any number above negative 1.645, we are not going to reject the null hypothesis, right? So this leads us to determine what we know as a rejection or a decision rule. And the decision rule is such that you reject the null hypothesis if the test statistic that you compute, okay, is what? Is less than the critical value that you have here. Okay. Now, let's go back to the question. Is the population standard deviation known or unknown? The population standard deviation known or unknown?
Jose.
Yes, Samuel. Is the population standard deviation known or unknown?
Jose.
Hello? Yeah, Emmanuel. Is the population standard deviation known or unknown?
Yes, please. I think it's a 0.8.
Yeah, is it known or unknown? That's what I want to find out.
It is known. It is known. Sorry.
If it were unknown, they wouldn't have given it to you in terms of sigma. They would have said maybe.
Yes.
So the moment you know it's, yes, it is known, that 0.8 is actually the population standard deviation. So what it means is that when we come back to this point, right, we want to see that indeed the population standard deviation is known. So the test statistic is a Z distribution, and that is why we computed the critical value from the standard normal distribution. Okay, if it were unknown, the sample size was small, we would have computed this test the critical value from a different distribution. Okay, which we will term as the T distribution. We'll get there when we have an example of that sort. Okay, Ima, once you are here, let's continue with the solution. Okay, I think Maureen is right. Okay, so we have a rejection rule. Okay, and the rejection rule indicates that we're going to reject the null hypothesis if how do you call it, the test statistic that we have calculated is what, less than the Z alpha.
Less than, yes.
So if there is any other thing, we are going to reject the null hypothesis. Okay. So now we are in a position to calculate the test statistic. Right. Okay. What's the sample size?
100.
Sample size is 100. What does the sample mean?
2.84.
And then the population standard deviation is what? Is
0.8.
So what it means is that we can now find the test statistic. In some books, they call the test statistic T, big T. Okay, either way, it's the same thing. So the test statistic was that X bar minus mu divided by what? Sigma divided by the square root of n, right? What is X bar? Is 2.84 minus 3, right? Divided by 0.8 over the square root of 100 is 10. So that whole denominator becomes 0.08. So when you add that, what do you get?
Negative 2.0.
Negative 2.0. Now let's see something here. Emmanuel, if you have this, the normal distribution, right?
Yes, please.
Okay, sorry for the way you can draw it better. Okay. Yeah. Something like this. And then the critical value was here, right? 1 point what? 1.645, right? 645. It was negative, right?
Yes.
1.645, so negative. And we calculated our test statistic to be negative 2.0. Would that negative 2.0 be within the rejection region or to be within the
within the rejection region?
Will be there because negative 2 is actually smaller than negative 1.6, right?
Yes, please. Yes.
The 2 falls somewhere here, isn't it? The minus 2 falls somewhere here. So what it means is that since the 2 is less than the 1.645, what do? It falls within the rejection region. We reject the null hypothesis, right? Now that we have rejected the null hypothesis, how do we conclude? Can you show us how we will conclude?
I think the conclusion would be that since we have been able to prove that the null hypothesis which was given is not true, then the average mean is not greater than 3, but rather less than 3. It's not greater or equal to 3, but it's rather less than 3.
So we are going to conclude and make our deductions in relation to the hypothesis that we formulated. You get it? So
yes,
we see that this one has been rejected. This claim,
yes,
this one has been rejected, and this one has been what? Retained.
Okay.
That's we are moving with. And what is this? This one says that the average TV number of TV sets is what? Is less than what? It's less.
Less than 3.
So you can conclude that there is not, or there's enough evidence to prove that the average TV set in Ghanaian homes is what? Less than what? 3.
Less than 3. Okay.
Or you can conclude that there is not enough evidence to show that the average number of TVs in Ghanaian homes is what? Is at least
Actually, greater than 3.
exactly greater
Okay.
than 3.
Equal
So
to 3. Yes.
basically, that is how we would look at the how do you call it, the hypothesis test procedure.
This is testing.
Asking whether Z is also known as the critical value. The critical value, the Z that we talked about, these are very notation issues. This Z here is a test statistic. In some books, they call it T. I can call it F. I can call it G. I can call it any letter that I want. Okay. But the critical value is mostly represented by setting the distribution and then the level of significance. Okay, so the critical value can be termed as Z alpha, okay, for a one-tailed test, or it can be termed as Z alpha over 2 for a two-tailed test. Okay, so those are the differences. If the test was a T distribution, I can call this T alpha or T maybe alpha over 2, then what we call the degrees of freedom, which we would have a look at. Okay. Okay, so we want to continue with where we left off from, and we want to consider another example, which in this case we want to use a two-tailed alternative. So what we've been doing is just being able to formulate and then test hypotheses. Okay, and all that we've been interested in is to test our claims from on the population based on certain sample data. Okay, we consider the one tail test, the upper tail and the lower tail type of questions, and we couldn't do the two tail test because of time, and we want to continue with that. So basically, the two tail test is when you have the null alternate hypothesis having an equal to sign, and then the alternate hypothesis having a not equal to sign. The approach to calculation is basically the same. So if you couldn't get the approach to solving and to calculating in the earlier lecture, you should be able to get it now because the approaches are the same. So you wouldn't really there's not any much different that we want to do today. So just take note of that and you would be fine. Okay, so let's have a look at this example. And then one thing we've also considered, you see, in the examples and in how to identify your test statistics, the distribution that follows the test statistics is either a standard normal distribution, which we normally call the Z, okay, or the T distribution. Okay. Now the Z distribution is used in identifying our critical values on two occasions. Number one, when your population standard deviation is known, and when your population standard deviation is known and then even unknown, and then the sample sizes are large. Okay. And the only time for the purpose of this course, the only time we'll be using a T distribution to determine our critical value and to help us to calculate is only when we have smaller sample sizes and unknown population variances. Okay, smaller sample sizes, unknown population variances, or standard deviation, however you would put it. So please take note of that. So basically, what we are going to do is we are going to do a two-tailed situation, and we're going to use the t distribution to solve that. I think from that you will be able to go through with whatever we have. Okay, so let's take the example. This is where we left off. The average cost of a hotel room in New York is said to be $168 per night. A random sample of 25 hotels resulted in by X, that is the mean, being equal to 172.5, and then standard deviation of 15.4. Now, we want to test at the alpha level. This time, we are just testing whether the average cost of the hotel room is 168 or not. You remember in this question, we've not stated anywhere whether we are testing as whether the hotel room is bigger than 168 or is smaller than 168. We are just interested in whether the hotel room is $168 or not. Okay, so in our formulation of the hypothesis, what we are going to do is to indicate that H naught or the null hypothesis is such that mu is equal to 168, and then the alternate is such that mu is not equal to 168. Okay, so once you have that, then you have it at the back of your mind that this is really a two-tailed test. Okay, now we are going to use the steps that we identified in determining hypothesis testing to do this. So the first thing we would look at is, of course, let's identify our variable of interest. Okay, so our variable of interest is basically the average cost of the hotel room, the average cost of the hotel room. Okay, then you identify or you specify the hypothesis, and the null hypothesis is such that mu is equal to $168, and then the alternate hypothesis is such that mu is not equal to $168. Now, the next thing we have to do is, of course, we specify our parameters. We know that the alpha is 25, the sample size is 20. Alpha is 0.05, and then the sample size is also 25, right? So basically, that is what we have. What we are going to do is, I want to ask you this. Is the population standard deviation for this question, is it known or unknown? Can anybody help us? Is the population standard deviation known or unknown? Is the population standard deviation known or unknown? Okay, so I have two separate answers. Some are saying known, some are saying unknown. Please read the question well. I mentioned to you that if the population standard deviation is known, the symbol is sigma, right? And then the symbol for sample standard deviation is S. If you look at the question, what do you see? Is it an expression that shows that the population standard deviation is known, or is that which shows that it is unknown? Yeah, I think the population standard deviation is unknown because we don't know it. What we are doing is we are using the sample standard deviation as an estimate for the population standard deviation. Okay, so population standard deviation is actually unknown. So what we have estimated is the sample standard deviation. Very good, Eunice. S for sample. Thank you. So what we want to identify is this. What about the sample size? Is the sample size large or small? Is the sample size large or small? Okay, very good. Very good. But as I mentioned, in some books, they will consider this sample size to be large because it's 25. But for the purpose of this course, let's let's take this sample size to be small. So when we are dealing with such a small sample, then what it means is that the critical value that we are going to use to or the distribution that is going to help us to identify the critical value will no longer be a z, okay, but it's going to be what? A t. That is what we are going to do. Okay. And because it is a two-tailed test, okay, the alpha or this level of significance is going to be divided by 2. That means one half occupies one part of the distribution table and then of the distribution curve, and then the other half occupies the other part of the distribution curve. Okay. So if you look at this solution, okay, you'd realize that if we have the distribution curve in this way, okay, then we are saying that because it's a two-tailed test, it's either because you know that it's bi-directional. We don't know the direction yet, so it can either be on the left side, that is less than $168, or it can be more than $168. So we share the level of significance among the two parts. Okay, so one part takes one half, and then the other part takes the other half. So you'll be interested in those two parts. And then the critical value or the distribution that will help you to identify this, as we said, because the sample sizes are small and then the population variances are unknown, what we are going to use is the T statistic, okay? The T statistic, that is the T distribution to do it. Now, the T distribution comes with two parameters. The first one is the sample size, which is n. Let me take it again. The T distribution comes with two parameters. The first one is the level of significance, okay, the level of significance. And the second part is what we call the degree of freedom, okay, the degree of freedom. You can repeat after me. Say it, degree of freedom. Very good. So what the degree of freedom helps us to do is to help us to identify the actual value or to identify the critical value. We are not going to go deep into the concept of degrees of freedom. That will take another lecture. So we will just use it as it is. But the degree of freedom will be identified in the T distribution at the sample size minus 1. Okay, so every T distribution table has an alpha and then a degree of freedom. Okay, and you see that as we move on. So what we are going to do is that we are going to find a T distribution, okay, that has an alpha value, and then it has a degree of freedom also attached to it. Okay, so let's take a look at this T table. Now, you see that we are interested in two things. Either for this T table, it's showing us both one-tailed and two-tailed probabilities. Okay, now as you can see, a two-tailed alpha of 0.05 corresponds to a one-tailed alpha of 0.025. Okay, so if the two table that you download has two values of alpha, like the way this is structured, then it means that if it is two-tailed alpha, this question, for the purpose of this question, we are choosing this 0.05. Okay, but mostly if you have a a T table that has only one value of alpha, it is mostly determined by the one-tailed alpha. So instead of choosing 0.05, you choose 0.025. This question is actually telling us to choose an alpha of 0.025 because it is 0.05 that has been slashed into 2. So what you just do is to locate the alpha value, okay, and the corresponding degree of freedom. I mentioned to you that we have a T distribution okay, a T distribution that has an alpha over 2, and then we have an n minus 1 degree of freedom. Okay, this is the kind of distribution that we are dealing with. Okay, this is the distribution that we are dealing with, T alpha over 2 n minus 1. Now, from the T table, we can read this. You can read this from the T table. And if you check, so we have an alpha of 0.025. For now, I think we should forget about the two-tailed alpha for now so that we can be consistent with our calculations. We have an alpha of 0.025, and then we come down and look for, we come down and look for the 24 degrees of freedom. So that gives us 2.064, this value. So 2.064. So what it means is basically this. The Z value that corresponds, or the T value, the T value that corresponds to an alpha of 0.025 is either negative 2.069 or positive 2.069. Okay. Once you've been able to identify your critical values, you should be fine. Okay, so if you have that, okay, if you have that, then you can find out what these critical values are, and then you compare. Now, the next step that we wanted to look at is to calculate what we call the test statistic, right? Calculating the test statistic. And the test statistic is calculated by using this relation. Remember, I mentioned that we are dealing with a situation where population standard deviations are unknown and the sample sizes are small. So number one, we've used the population mean, the sample mean minus the population mean divided by this formula. And what we've done is to use the sample standard deviation as an estimate for the population standard deviation. Okay, so basically what you would see is we have the sample mean, which was given in the question as 172.5, right? So you have the sample mean as 172.5 minus the population mean, which is the hypothesized value, okay? The hypothesized value divided by the standard error, that is giving us 15.4 divided by the square root of 25, and that gives us 1.46. I remember that the decision rule that we have, okay, is that we are going to reject the null hypothesis when the test statistic that we calculate falls within the critical region. Okay, so for this question, I would have indicated my decision rule to be this. We're going to reject the null hypothesis, or reject H0 if your test statistic, the one you calculate, the test statistic, is actually less than minus 2.064, or the test statistic is actually greater, so it's less than, it's less than 2.064, or is greater than positive 2.064. Right. So basically, this is what we have as our decision rule, and that is what we are going to stick with for now. But when we calculated our test statistic, what did we get? We got 1.46. Okay, the test statistic was 1.46, and so what it means is that the test statistic that we have here, it's really check whether it's within the rejection region or the acceptance region. This 1.46 is not smaller than negative 2.06, neither is it bigger than 2.06. So it lies within the acceptance region, and it means that we do not reject the H0, okay? So if you do not reject the null hypothesis, then you conclude, the conclusion is that there is not enough evidence to show that the true mean cost is different from $168. So basically, this is what we have. And I'm going to summarize the steps once again for the hypothesis testing for you. So in the course of summarizing, these are the basic steps that you need to do. So the first one is identify the parameters of interest, right? Identify the parameters of interest. So this is where you say that let mu or let mu be the mean, then you go on blah blah blah, then you state that. And the second step is where you specify the null and alternate hypothesis, right? Yeah, so this is where you indicate that H naught is such that mu maybe is equal to something something, and then HA or the alternate hypothesis is such that you indicate that. Now, the third is what you would do is that the third step is for you to identify, right? Identify the critical value and the critical region. Now, this is where you would either check whether it follows, whether data, let me put it this way, whether data follows a Z or a T distribution, right? And we indicated that is a Z distribution, right? If population Z, so if population standard deviation is known, right? If population standard deviation is known, we use a Z, right? If population standard deviation is unknown and sample size is large, right? We use a Z. We still use a Z. Okay. Then if population standard deviation is unknown and sample size is small, then we use a T. So the only time we are going to use a T for this course is this situation when the population standard deviation is unknown and then the sample size is small. Well, okay, so that is going to help you to identify the critical value or the critical region. What you also need to know is to take notes, right? Take note of the alpha value. The alpha value will also help you to identify your critical region and whether the test is one-tailed or two-tailed, right? Now, once you've been able to specify or identify your critical value and the critical region, the next step for you is really your ability, you actually have to make, how do you call it? Specify the decision rule, okay? Specify the decision rule. That is, once you find the critical region, then you know that, okay, you reject the null hypothesis. If so, reject the null hypothesis or reject H0 if maybe test statistic is less than this value or is greater than that value. Then you calculate the test statistic, right? Calculate the test statistic. Then you make decision and then conclude. Okay, make decision and conclude. This is a very simple approach to solving your hypothesis test questions. It's very straightforward, very simple, and I hope you would be able to take note of that, and then you will do it. I mean, these are not hard and fast rules, okay? These are not hard and fast rules, but it will help you in your approach to learning the concept of hypothesis testing. Okay, so let's move on to the the continuation of our work. Okay, now what we've done basically is to do a test of hypothesis for means. Okay, and we can also do a similar test of hypothesis for proportions. Okay, because sometimes the conclusions and then the inferences we make are for population proportions instead of are based on proportions instead of just based on averages. Okay, so when we are dealing with proportions, how do we test our hypothesis when it comes to proportions? It turns out that it's the same way, it's the same approach to testing hypothesis for means, just that the only difference is how to calculate the test statistic, okay? How to determine the test statistic. So hypothesis testing for proportions, I mean, it still involves categorical values. There are still two possible outcomes, either a success or a failure. And we are interested in the fraction of the population in the success category. Basically, what we are interested in is the proportion or the group, the portion of the population that has a certain specified attribute. So if someone just says that unemployment rate is 20% or is 30%, that person might have used a sample to determine this unemployment rate, and that person has to test that. Okay, so that is what we are interested in testing. So we know these things that remember sample proportion, we are going to represent it using the p bar. Okay, sample proportion that we are going to represent it using the p bar. So we know that the sample proportion is just identified by the number of successes in the sample, as in the people with the required attributes in the sample divided by the sample size, right? And we need to get to know that P and NP and N1 minus P should be at least 5. We saw this when we're dealing with sampling distributions, okay? And we can approximate this using the normal distribution, where our mean is actually the population, the sample proportion, and then our standard deviation can also be given as this. We saw this when we were dealing with sampling distributions, I think a week ago, right? Okay. Now, we are just going to discuss only one aspect. In the test of means, we discussed 3 situations, right? But in the test of proportions, we are just going to discuss only one situation. The rest is beyond the scope of this class. So what we are going to do is we are just going to look at the situation where NP is greater than or equal to 5, and then N minus P, N into 1 minus P is also greater than or equal to 5. The other side, we are not going to look at it. Okay, so maybe that's hallelujah for you. All right, so that is what we have in specifying that the distribution is a normal distribution. Okay, because it follows, or it has met these 2 criteria. So basically, we are going to use a standard normal table or a Z distribution, and the test statistic is identified as the p bar, which is the sample proportion, minus the p, where the p is actually the hypothesized proportion. Then we take the standard error, which is p bar into 1 minus p bar divided by the square root of n. Okay, so we have we would take an example, and then we will solve it based on how we want to do. Okay, so a bit of a correction here. In testing in testing for Z, it's actually not p bar. Okay, this p bar should not exist. So it's just supposed to be p into 1 minus p. We are going to use the hypothesized value to determine the standard error, not the sample value. So this is devoid of p bar, and I think it will be corrected before the slides are sent to you. Okay, let's take a look at an example. So we have a marketing company that claims that it receives 8% of its responses from its mailing. It receives 8% of its responses from its mailing. To test this claim, a random sample of 500 were surveyed with 25%, with 25 responses. Test at the alpha level equals 0.05. Test at 0.05 level of significance. And before we even move on, we have to check whether NP is less than or equal to 5 or it's greater than or equal to 5. So when we check our N, which is our sample size 500 times the P of 0.08 is actually 40, and then the N into 1 minus P is actually 460. So we are good to go. So we can apply the knowledge of hypothesis testing for this particular problem. So remember that we are testing whether it receives 8% of its responses or not. So our null hypothesis involves not just an inequality. It doesn't involve an inequality. It involves equality. So our null hypothesis is such that P is equal to 0.08, and then our alternate hypothesis is such that P is not equal to 0.08. So we have a two-tailed test. Okay, we have a two-tailed test. Of course, based on the assumptions that we had earlier, we know that this is going to be a standard normal distribution table. And based on the test, okay, based on the test, you would realize that first of all, we've identified our parameters of interest, and our parameter of interest is the proportion, okay, the proportion of responses that the marketing company receives from its mailing list. Then specifying the null and alternate hypothesis. I think we've done that. H naught is such that the proportion is equal to 0.08, and then HA is such that the proportion is not equal to 0.08. Very good. Then the third step for us is to identify the critical value and the critical region. Okay. Now we've seen that we are dealing with proportions, so we are not going to ask ourselves whether the sample standard deviation is known or the sample standard deviation is unknown, or whether sample size is small or the sample size is large. For a proportion, what we are just going to deal with is the Z distribution. And we are dealing with that because we've already provided this check to show that indeed we can approximate this distribution to a standard normal distribution. Okay, but we know that its alpha is 0.05, but we are dealing with what? A two-tailed test. So we're going to divide alpha into two. One part takes one half of alpha, and then the other part takes the other half of alpha. So we are going to have minus 1 Z, the critical value will be Z alpha over 2 minus Z alpha over 2 on the left side, and then of course we have Z alpha over 2, right, on the right side. And if you would look into the normal distribution table, okay, we are looking for either 0.025, or on the right side we are looking for 0.975. Okay, it's easier to look for 0.025. So if I come to my normal distribution table here, I don't look at the sides, right? But I go deep into the pool of numbers to identify which Z value corresponds with a probability or an alpha value of 0.025. So let's see. We have 0.00, it goes on here. Good. We have 0.02559, and then we have 0.02500. That is very, very accurate. Like, it's hard to get figures like this. And the z value that corresponds to 8 is minus 1.9 on the side, and then 0.06 at the top, right? Minus 1.9 on the sides, and then 0.06 at the top. So that gives us, thank you, that gives us 1.96. So it's actually minus 1.96 or positive 1.96. Now, what you can do is basically in hypothesis testing, there are three main values of alpha that we normally would give you. The 5%, 10%, and then 1%, right? So every value of alpha has its corresponding z value. So you should be able to know which z value, which z score would correspond to these values of alpha, so that you don't always go back to the table to calculate it, especially if you are working under some we are working under time, time constraints and time restrictions. So for instance, I know that z 0.025, okay, is plus or minus 1.96. I know that z 0.05 is plus or minus 1.645. So once I have those in my mind, I wouldn't have to go back and read from the table to identify what those values are. Okay, so you can make a summary of all potential z values, and you use it in identifying the critical region and the critical value. Okay, so once we've identified the critical value, we can now identify the critical region. So the critical region will be this: any number below negative 1.96 or any number above positive 1.96 forms our rejection region. Then we can move to the other step of specifying the decision rule. And that means that we are going to reject the null hypothesis, right? If the test statistic that we calculate is less than negative 1.96, or if the test statistic that we calculate is more than positive 1.96. Okay, so when we calculate the test statistic for this question, and remember that I said it was p minus p bar into p into 1 minus p. So the correction has been done here. Okay, so just take note of that. The correction has been done here. Then what it means is that it's going to be 0.05 minus 0.08, the hypothesized value, divided by 0.08 into 1 minus 0.08 over 500. That gives us negative 2.47. Negative 2.47. And if you compare, you realize that negative 2.47 lies within the left side of the critical value. So it's actually smaller than minus 1.96. So it finds itself within the critical region. And since it finds itself within the critical region, our decision is to reject H0, of course, at alpha equals 0.05. And then we make a conclusion. And the conclusion is that there is sufficient evidence to reject the company's claim that there is an 8% response rate. As you can see, the response rates, the evidence that we have do not warrant that claim that there is an 8% response rate. Okay, so basically that is it for the hypothesis test. All right, Eunice, thank you. So that is it for the hypothesis test. There's also another solution approach. That's the p-value approach, but I'm not going to consider that for now. I think that you'll be doing more of p-value approaches to hypothesis testing when you guys are doing research methods next semester. So I would not spend so much time on that. We would quickly move on to what we have to do for today. Okay, so are there any questions or any worries for this before we move on?